So we're going to review some concepts and ideas that were discussed in the previous session. Okay, review. The last thing that we did is we were able to define open sets in a metric space. So here you get a metric space X. Okay, and you get a subset U of X. When can we say that a set is open? Sabi natin, U is open. Okay, if for every X or for every point X that can be found in U, there must exist an open ball centered at X of some radius that will fit entirely in U. So that's the English version. But that means in mathematics, that means that you can find some radius, some positive r greater than 0, such that once you constructed the ball around X with radius r, that ball fits entirely in the set U. So if this is your set U, pag sinasabing open yan, kailangan pag kumuha ka ng X dyan, makakagawa ka ng some open ball around it. No, syempre yung bilog na ball, that's only my representation. But as you can remember from last lecture, balls need not be really round. Kaya lang ating representations normally kapag mga pictures na ganito are circles kasi sila yung madaling i-drawing. Okay? At isa pa, ito yung tinatawag nating standard metric, under the standard metric. Yan. Kailangan lang kapag pumili ka ng kahit na sinong point na nandoon sa U, makakagawa ka ng open ball around it so that that open ball is still part of the given set U. This is why when the set is open, hindi pa pwedeng kasama yung nandito sa gilid o yung nandun sa boundary na tinatawag natin. Kasi alam nyo, kapag when you consider the points that are on the boundary, buburahin ko yung boundary ha, gagawin ko on dashed so that it indicates na hindi kasama. Kasi kapag pumili ka ng point that is in the boundary, as you can see, no matter how small the radius or the ball that you will construct centered at X, no matter how small that ball is, hindi yan makakapasok doon sa given na set U. Kaya kapag ang set O ay open, ang ating intuitive idea, set siya na walang boundary or walang balat. Okay? Ang kasama lang dun sa set, yung mga nasa loob. Hindi kasama yung nasa gilid. Pero technically, kapag sinabing mga points na nandito sa open ball around X, ang ating interpretation yan talaga in terms of metric, ito yung mga points na malapit doon sa X. Na kapag ito yung X, yung mga points na nandito sa open ball around X, they are thought as the points that are near X. No? Sila yung malapit dyan sa X. Kaya kapag babasahin niyo ulit itong definition ng pagiging open, no? Parang sinasabi niya that a set is open if whenever a point is in the set, then the points near to that point must still be in the set. Kailangan hindi lang siya ang nasa set, pati yung mga kapitbahay niya nandun pa rin sa set. If you can see that. Na may mga properties na dapat lagi niyong alam ang mga open sets, no? Number 1, yung space X itself and the empty set, no, are technically the basic open sets. Okay? Ano pa bang example? Yung mga open balls themselves are open sets. Prove din natin yun. Pangalawa, ang arbitrary unions of open sets are open. Ano yung sabihin ko ng arbitrary union? Kahit na ilang open sets yan, if you have a bunch of open sets, when you take their union, the union is still or remains open. Pero pag intersection, as we have noted, mag-iingat kayo, no? Only finite intersection ang certain tayo na magiging open, no? So let me write here finite intersection of open sets are open. And when we say finite, kahit na 1,000 open sets yan, no, kunin mo intersection, the intersection will still be open as long as it's finite. Kapag infinite na, as you can see, hindi yun laging masasabi. We had a counter example last time. No? Meron tayong example when you get a bunch of open sets, an infinite collection in fact, then when we took the intersection, we ended up with a set which is not open. So in other words, the same thing cannot be, the thing that can be said for union cannot be said for the intersection. Pagdating sa openness, um, mas strict tayo sa intersection kaysa sa union. That's the idea. So for today's lesson, we will continue studying metric spaces. But magko-focus tayo dun sa analytical properties ng metric spaces. Kapag sinabing analytical or analysis, ito yung mga concepts na may kinalaman sa analysis. For example, yung idea ng convergence, yung continuity, yung mga ganyan. So, ang unang definition for today, so we will define when is a sequence of points in a metric space converges to a given limit. Excuse me. Medyo sinisipon ako. Okay. So this is how we define it. So a sequence, so you get a sequence of points in the space X having a metric D. This sequence converges to a point X, which is called as the limit of the sequence. And we write it in this manner as always, or you can choose to write it in the following form. If ang ating definition, as before, no, ganito rin yung definition sa calculus, except ang change lang na ginagamit dito is this, no? The way we will measure the distance between points is using the metric D. Okay, so sabi, if for every epsilon greater than 0 to every epsilon greater than 0, a natural number n can be selected in such a way that whenever an index little n exceeds this capital N, the distance from xn to x can be made less than epsilon. So, ibig sabihin, kapag magsaset ka ng kahit na anong positive na epsilon, no matter how small, dapat there will come a time so that beyond that, na paglagpas nung time na yon, yung distance nung xn tsaka nung terms na sequence mo from the supposed limit is already smaller than epsilon or is already small. Sabihin, malapit na ito sa x kung yung subscript niyan ay malaki na. That's how we think about the definition. Or pictorially, if by the way, if you are going to look at this also means, or it's equivalent to saying that distance from x of the terms x sub n is getting 0 kasi it can be made arbitrarily small, diba, for large indices. So that means to say that the sequence of real numbers ngayon to, distance kasi yan. This sequence of real numbers converges down to 0. Sabihin yung distansya ng xn from x, kailangan lumiliit sa 0. And for some picture or some pictorial reference, let's say this is x. How do you know that a sequence converges to x? Kailangan, pag nag-drawing ka ng epsilon radius, no, as in the picture, at ginawa mo yung epsilon ball around x. So this is the neighborhood of x or the ball around x, no, with radius epsilon. kailangan yung terms of sequence mo, hindi natin nire-require. Take note, the definition does not require that every term is in this ball. Kailangan lang, after some time, no, after some large index, yung x sub n mo, capital N, index will already be inside the epsilon ball. At paglagpas pa niyan, hindi na makakalabas dito. No? All the points that are with subscripts bigger than capital N, kailangan nandito na sa loob at hindi na makakalabas. So in other words, parang you can think of the subscript as a measure of time, no? Kung kailangan laging mayroong instance, kahit gaano kaliit itong epsilon, kailangan laging mayroong instance where after that instance, yung mga terms mo, nandito na sa loob ng epsilon ball. Ano pa ba? As you can see, if you are going to measure the distance of every term from x, as you can see, yung distansya na yan ay papaliit ng papaliit as noted in this remark. Did you understand? Naintindihan niyo ba? Okay. Let me continue. The first remark that I'd like to show you that in a metric space, this is important. Ha? Kaya ako binigyan to ng highlight. Kasi later, when we talk about a more general space, yung tinatawag nating topological space, which is the main topic of this semester. Makikita nyo in a general topological space, ang mga sequences pag nagko-converge, hindi necessarily sa isang lugar lang. What makes a metric space special is the fact that if a sequence converges, ang limit palaging unique. In fact, nasanay kayo all your life, no? All your life, nung nag-aaral kayo ng calculus, no? Ang limit ng kahit na ano, kahit na function, kahit na sequences, ang limits palaging unique, isa lang, no? But you will find later that in a more general topological space na tinatawag natin, sa general topology, ang limits ng mga convergent na sequence ay hindi palaging unique. Pwedeng ang isang sequence mag-converge sa dalawang points, no? In some space, no? But in metric space, hindi yun mangyayari. The reason for this lesson, actually, di ba, yung buong slide na ito, dinidiscuss mga metric spaces. The reason for this lesson is to give you a solid reference or foundation, if I may say, so you can compare the concepts that we will be discussing later. Ano yung, kasi parang sinasabi ko sa inyo na yung mga metric spaces, sila yung standard. I mean, ito yung kinalakihan yung mga spaces. Right? Whereas, yung mga properties ng metric space ay hindi pala universal. When we say hindi universal, may mga properties yung metric spaces na mapapansin yung, dati kapag metric space, totoo to, tulad na ito, no? Pero later on, makikita nyo, hindi siya necessarily true for an arbitrary topological space. Kaya nga exciting yung yung mga topological spaces. May mga results na very intuitive. When I say very intuitive, parang nararamdaman mo bakit totoo, no? Pero meron din mga results na counterintuitive. When you say counterintuitive, hindi quite unexpected kasi in normal situations like metric spaces, ito yung nangyayari. Pero pag sa general pala, hindi pala masasabi yun. So, kaya ako pinakita itong lesson na ito so you can make a comparison. So, why are limits in metric spaces unique? Oh, that's the question. So let me kind of explain why. Let's say, yung sequence mo nagko-converge sa dalawang points, sa x tsaka sa x hat. Right? Now, if you're going to look at the distance of x, so ganito, no? Ito kunwari yung x, ito kunwari yung x hat. Tignan mo yung kumuha ng isang term, yung sequence mo, let's say x sub n, excuse me. Please make sure na yung microphone ay nakamute. May marinig akong tao. Okay. What we're going to do is we're going to look to select a term and then look at these 3 points. And dahil may 3 points tayo, it is natural to think about the triangle inequality. So gagamitin natin yung triangle inequality in a metric space. Ito yon. Yung distance nito, hindi lalagpas if I add these two distances. Na pag pinagsama ko yung dalawang distances na to, no? Hindi yan, mas maliit palagi yung distance ng x hat. So that's the triangle inequality. And this is true for all n. Now, because of these convergences, kasi sabi niyo nagko-converge ito rin sa x hat. So by the previous remark, dapat ito nagpupunta sa 0. Dapat ito nagpupunta sa 0. If you have two real sequences, no, bawat term nung bawat sequence mo nagko-converge sa 0, yung sum nung dalawa as a real sequence, as you can remember from advanced calculus, will also converge down to 0. Diba? So therefore, this, no matter how large n is, it's less than or equal to 0. But the distance cannot be negative. So therefore, the only possible value for that distance is that it must be 0. And again, by metric space action, kapag ang distance ay 0, that means to say that the points are necessarily equal. So as you can see, when you look at the proof was made here just because yung D na ito ay mayroong mga properties katulad ng triangle inequality. Gumamit din ako ng symmetry dyan. Tsaka yung property na ang distance ay 0 if and only if the points are equal. Ginamit natin yung tatlong metric space axiom dyan ang hindi nyo na mamalayan. Pero this is to say na yun nga, yung proof nito or yung result nito is dependent dun sa fact na yung space ay may metric. Later on, when we talk about more general spaces, ang mga topological spaces need not have a metric in it. Hindi kailangan may distance. Kaya yun, makikita nyo, hindi ito necessarily mag-hold. Isa pa sa mga ideas na importante na magpe-play ng important role later ay yung idea ng mga Cauchy sequences. From advanced calculus, I think, there, una narinig yung word na Cauchy sequence. Kapag sinabing Cauchy sequence, the way I think about Cauchy sequences without knowing the definition. Let's say, hindi mo memorize yung definition. Kasi may mga students that are very good when you ask the definition, anong definition ng Cauchy sequence. Kaya lang ang problema, minemorize lang pala yung definition, no? For every epsilon. Pero kung ano ba talaga ang idea behind the concept of being Cauchy, hindi naman naintindihan. Pwede naman ma-state mo yung definition without really understanding. That's possible. Pero gusto kong maintindihan nyo dito, ano bang Cauchy sequence? Pag sinabing ang sequence ay Cauchy, what does that mean? It's named after Cauchy, no? Kasi si Cauchy ay isa sa mga founders ng analysis. Siya ang isa sa mga promotor. Ba't kayo may epsilon delta sa calculus, no? Kasi before Cauchy, calculus before was very intuitive lang, no? Yung pakiramdaman lang ang method. Yung calculus ni Newton at ni Leibniz. Until dumating si Cauchy, siya ang nagbigay ng mga formal definitions for limits, no? Etc. Yan. So in honor of his work, no, pinangalan sa kanya yung isa sa mga importanteng examples of sequences in analysis, which are the Cauchy sequences. Pag sinabing Cauchy, the way I think about this in my mind is that ito yung mga sequences that after some time, makikita nyo yung mga terms nagsisiksikan na. When you say nagsisiksikan, when you pick two arbitrary points from the sequence, and you find that the subscripts of these terms are large, no? If the subscripts of these two terms are large, as you can see, their distance is going to be small. Sa madaling salita, ang sequence ay Cauchy kung if the distance between two points, two terms with very large subscripts is small. Yun yung ating definition talaga. Ulit, kapag sinabing Cauchy, ang distansya ng dalawang terms ay maliit kung ang mga subscripts nila parehas malaki. So halimbawa, kinuha mo si x sub 1 million tsaka si x sub 5 million. No, dahil kung para sa iyo malaking 1 million at 5 million, dapat yung distansya nilang dalawa, makikita nyo maliit. And that distance keeps on getting smaller as the subscripts gets larger and larger. So you can imagine na nagsisiksikan yung mga points habang tumatagal. Naintindihan nyo? Now take note that this definition has nothing to do with existence of limits. Wala tayong pinag-uusapang limits kapag Cauchiness ang pinag-uusapan. Unlike yung word na convergent, di ba, para ang sequence maging convergent, dapat mayroong limit. Kumbaga meron kang isang point na tinitignan kung saan lumalapit yung mga points. Pero ang Cauchiness iba. You are just looking at the terms, pairs of terms in the sequence. Kailangan kapag kumuha ng dalawa, malaking subscript nila at yung distance nila maliit. Yun yung definition na ito. For every epsilon, there comes a time so that the distance between two terms is small whenever the subscripts are large. Ako kapag nagbabasa ako ng mga books analysis, that's how I read it. I don't really necessarily verbalize epsilon. Hindi ko verbalize yung natural number na n. Kasi kapag when you use these words, ang tendency is basahin niyo lang siya rotely, no, parang minimemorize niyo lang. Ako, basta may something less than epsilon, pinapalitan ko yun ng small. May something bigger than n, papalitan ko yun ng large. That's one way to read statements in analysis. Naintindihan niyo ba, sister? Naintindihan niyo yung point ko? Tinuturuan ko kayo kung paano magbasa ng mga definitions sa analysis. Okay? Naintindihan niyo ako? Yan. Kapag may something less than epsilon, palitan niyo yun ng small. Pag may something bigger than n, palitan niyo ng large. Okay. Kaya kapag pabasahin mo ito, tingnan niyo. For every epsilon greater than 0, there exists an n. Parang sinasabi niyan, if you fix a positive number epsilon, there comes a time so that two terms will be close to one another kasi small ang distance whenever their subscripts are large. Ayan. Equivalently, you can say that, a sequence is Cauchy if the distance between the two terms gets 0 as both the subscripts and an m gets larger and larger. Ayan. So the next question is, do you think may relationship yung pagiging Cauchy at pagiging convergent? Naturally, there is. Okay? Why? Kasi kapag convergent yung sequence mo, yung mga terms ng isang convergent sequence are getting closer to a point. And as you can see, if these terms are getting closer to a point, no? Imagine niyo, ito yung limit mo, ito yung terms ng sequence mo, papalapit ka ng papalapit dyan. Hindi naman kailangan straight, no? Kasi hindi naman straight line ng space natin necessarily. Yan, papalapit ng papalapit. Habang lumalapit sila sa limit, as you can see, they are also getting closer to one another. Kaya nga, the idea is, ang mga convergent sequences are naturally Cauchy. In fact, yun yung next na result. Excuse me. Naintindihan nyo intuitively why? Kasi kung ang mga terms mo lumalapit sa isang point, as they get closer to a particular point, which is what we call as the limit, they are also getting closer to one another, which is actually the idea of being cushy. Did you understand? But why is that correct? Yeah, hindi naman pa pwedeng ano, ganun lang lagi ang math. Remember, we are still doing math, so we still need to be able to translate this into symbols like this. So, kunwari nagko-converge yung x sub n sa point na x. So, what I do, kukuha ko ng dalawang terms ng sequences ko, ng sequence ko, which are x sub n and x sub m. Okay? Kasi ito yung limit. So yan, nakakita ka na naman ng tatlong points. So tandaan yan, pag kayo nasa metric space, nakakita kayo ng tatlong points. It is very common to apply the triangle inequality. Kailangan the next best thing na may isip nyo ay yung triangle inequality. If you look at the distance between these two, remember, you're proving cushiness. You're proving cushiness. Therefore, you may need to look at the distance between x sub n and x sub m as in the definition. Kailangan ito yung maging less than epsilon or kailangan ito yung lumiliit. By triangle inequality, it cannot exceed the sum of those two. But because the sequence is convergent to x, dapat ito lumiliit. Dapat ito lumiliit. Kaya yung sum na yan lumiliit. Kaya ito ay lumiliit din ng lumiliit habang lumalaki yung n at m. Therefore, that means cushiness. So that's I mean, ito yung palasak na proof eh. Pero yung actual na proof na ito, normally, we let an epsilon be greater than 0. Tapos, pipili ka ngayon ng n such that yung distance ng x sub n tsaka ng x, pipersahin mo maging less than epsilon over 2 kapag yung n greater than n. Bakit epsilon over 2 ang pinang-ipit mo? Para ito maging less than epsilon over 2 plus less than epsilon over 2 kung yung n at m malaki na sa capital N. Ito yung formal. In the end, ito naging less than epsilon. That's how you do it in a formal analysis class. Kaya wala naman tayo sa analysis class, so we will not do it here. Ang in-introduce ko lang sa inyo idea. Okay? So naturally, convergent sequences are Cauchy. Now this is the question. Are Cauchy sequences necessarily convergent? Kapag ba ang mga terms ng sequences ko ay lumalapit sa isa't isa in a metric space, kailangan ba nagko-converge yun? Kailangan ba mayroong limit? Naaalala ko yung teacher ko sa analysis when I was studying BS Math before. Sabi niya sa amin, imaginein mo, pag sinabing convergent, imaginein mo, mayroong dumating na sikat na artista, kunwari sa PUP. Yun yung example niya naalala ko. Parang may dumating na sikat na artista, nagpunta ng Lagoon, no? So, ang mangyayari, maraming fans, kunwari ng mga estudyante, magpupuntahan sila doon sa artista para magpa-picture. Yun yung tinatawag natin converge. Nagko-converge sila sa isang point. Now, as they converge, as you can see, nagsisiksikan ngayon doon sa Lagoon. That's cushiness. Kaya ang convergent sequences, cushy. Now, if you will ask me kung ang mga Cauchy sequences ba ay naturally convergent, the answer is no. Kasi hindi lahat ng nagsisiksikan may point na pinagko-convergent. For example, sabi niya, di ba sumasakay kayo na LRT, siksikan doon. Pero wala namang hindi naman kailangang may artista. Kaya kayo nagsisiksikan. Yun ang naalala ko sa teacher ko nung undergrad. So, I get to understand bakit pag sinabing Cauchy, hindi necessarily convergent. Pero mako-confuse kayo ngayon. Kasi sabi sa advanced calculus, ang mga Cauchy sequences daw ay convergent din. The thing is, true yun, correct, only when you are in the real number line. Kasi ang real number line is very much proper. No? Siya, magandang space yun. Nagagawa niyang maging convergent ang mga Cauchy sequences. Pero in general metric spaces, that cannot be said, as an example, here, I'm looking at the space Q. I mean, yung mga rational numbers lang. Huwag niyong tignan yung buong real number line. Imagine just the set of rational numbers. Ang metric natin yung standard na distance. Okay? Ang gagawin nyo, for each rational number, ganito na lang. Tingnan niyo yung square root of 2 sa number line. Tapos, tingnan niyo yung square root of 2 plus 1. Siyempre, pag nag-add ako ng 1, nasa kanan yun. May theorem kayo sa advanced calculus dati. Sabi niyan, sa gitna ng dalawang real numbers, laging may rational number. Density theorem yata ang pangalan nun. So, therefore, I can pick a rational number R1 between square root of 2 and square root of 2 plus 1. Ha? Agree? Type 1 if you agree. Kung naaalala niyo yung density theorem na yan. Naalala niyo? Type nyo nga 1. Okay. Next. Instead na mag-add ng 1, mag-add ako ng 1/2. Pag nag-add ako ng 1/2, medyo liliit yung distansya, of course. Because kanina ang distansya ay 1, ngayon ang distansya ay 1/2 na lang. Sa gitna na itong dalawa ngayon, meron ulit rational number. Tatawagin ko yung R2. Then I will keep on doing this. Mag-add naman ako square root of 2 plus 1/3. Makakabili na naman ako ng another R3 na rational. In the end, what we're doing is we're picking a rational number Rn that falls between square root of 2 and square root of 2 plus 1 over n. And by the squeeze theorem, it should be noted that because 1 over n converges down to 0, yung r sub n may ipit, no? Mapipilitan siya mag-converge sa square root of 2. As you can see in the picture, totoo naman, diba? Hence, dahil convergent siya in R, it must be Cauchy. So in other words, si R sub n is Cauchy in R. And because all of the terms of Rn is rational, it is also Cauchy in Q. Kasi lahat ng terms niya rational numbers. Wala naman tayong piniling hindi rational. So you can say that this sequence is a Cauchy sequence in Q. But as you can see, this sequence, however it does converge in R, in fact to the square root of 2, it does not converge to Q. Kasi ang limit niya, hindi pa pwedeng maging rational number. Ang limit niya actually ay square root of 2. So, ang nangyari dito, we were able to find a Cauchy sequence of rational numbers that does not converge to another rational numbers. Sa totoong buhay, or in reality, hindi siya nag-converge, hindi dahil wala siyang limit. Meron siyang limit. The problem is your space. Ang may limitation dito ay yung space na pinag-uusapan natin. Because if we were to include the square root of 2, meron sanang limit yung sequence na to. Kaya lang, Q has no square root of 2. Diba? Naintindihan niyo si sir? So, ang reason kaya itong Cauchy sequence na to hindi nag-converge, hindi dahil hindi magko-converge yung sequence. This sequence is ought to converge. The problem is the space. The space itself, butas-butas ito. No, butas-butas ito. Sa topology later, kapag nangyayari na ang mga Cauchy sequence ay laging nagko-converge, no, in your space, we say that the space is complete. Complete, yun yung ginagamit na term. Kaya nga ang real number line, complete yun. Kasi ang mga Cauchy sequence of real numbers, laging nagko-converge. Which cannot be said for the space Q. Kumbaga, hindi ka nais-nais na property yan ng mga rational numbers. Kaya alam niyo, mga rational numbers, iniiwasan sa analysis kasi, yung space Q, kasi it cannot provide limits to every kind of sequences that is ought to converge. No? Magko-converge yung sequence pero napigilan sa pagko-converge dahil lang sa structure ng Q. Ayan. Kaya nagkaroon tayo ng completeness. Ang space ay complete if and only if every Cauchy sequence in that space converges in X. Kaya itong si Q, hindi complete. Pero if you look at the real number line under the standard metric, yung normal na distance, okay? Every Cauchy sequence of real numbers is convergent. We call this as the completeness theorem, no, sa advanced calculus. And I do not want to talk about this here. No, I mean, kasi ito ay something that you have taken before. Ang idea dito, if you are going to recall the proof, if I can recall the proof, gagamitin mo dito yung sinatawag na Bolzano-Weierstrass theorem, that if a sequence is bounded, it has a convergent subsequence. Kumbaga yung proof na ito ay dependent sa Bolzano-Weierstrass theorem. But the Bolzano-Weierstrass theorem, if you are going to trace back, nakadepende naman siya sa tinatawag na nested interval property. Si nested interval property ay dependent naman sa monotone convergence theorem. May mga theorem sa advanced calculus, if you can remember. Tapos yung monotone convergence theorem, nakadepende siya sa tinatawag na completeness axiom. Actually, everything in calculus when it comes to limits ay nakadepende sa completeness axiom. Ano yung completeness axiom? Any non-empty set that is bounded above has a least upper bound. Napakasimple ng statement na yun, pero alam nyo, yan ang foundation ng calculus. Without the completeness axiom, there's no calculus at all. Itong parang yung, kaya ang analysis, sa point of view ng mga mathematicians, ang analysis hindi masyadong maganda ang foundation. Alam niyo bakit? Para siya isang bahay, malaking bahay, na ang pundasyon niya ay isang theorem lang or isang axiom lang. Isa lang yung pundasyon niya samantalang ang laki-laki ng buong bahay. Kaya ang analysis is prone to be contested, yung mga results analysis, no? Kasi nga, ang kanyang foundation is very, pwede na sabing weak. I don't like to call it weak, but rather, very simple yung kanyang foundation, which is what we call as the completeness axiom. Anyway, kanina pa tayong mga open sets, no? Kailan naman ang set closed? Na ito, yung maraming students na nako-confuse dito. Kasi ang definition natin ng closed, ganito. A set is closed if its complement, this is the complement of f in x. I don't like to use this. Di ba? May ganyan kayo notation. I normally would use x minus f instead of f prime or f complement. Kasi, alam nyo, may issue ako sa paggamit ng ganito or nung ganito, no? Kasi, pag sinabing complement ng f, ito yung mga bagay na wala sa f. O, halimbawa, ang universe natin ay real number line. Ang f kunwari, mga rational numbers. Maliwanag yung r minus q. Alam mo nito, mga irrational numbers lang. Di ba? Mga irrational numbers. Pero kapag sinulat nyo q complement, ano-ano yung mga nandito? Parang hindi siya parang hindi siya malinaw. Kaya, I mean, malinaw. Parang pwede pong isipin na halimbawa, ang kalabaw hindi naman siya rational number. Pero ang kalabaw ba nandito? Hindi natin intention yon. Hindi natin intention na isama yung kalabaw dito sa complement ng Q. To eliminate this confusion, I'd rather use R minus Q instead of Q prime or Q complement. Kasi napakaraming bagay sa mundo ang pwede mo ilagay doon sa complement ng Q. Kaya kung prefer dito kasi maliwanag kung ano yung universal set. Kasi sinulat mo lang Q complement. Ano yung universal set? Kailangan mo pang specify. Naintindihan nyo? That's why I prefer this instead of using the complement notation. Okay, so a set is closed if its complement is what? Is open. Ang nalilito yung mga estudyante dito, ang set, karaniwan, kapag ang set ay hindi open, iniisip closed. No. Ang pagiging closed, pagiging open, ay hindi mga complementary statements, no? When say hindi complementary, hindi yan switch ng light na on at off. As you will see later, there will be sets which are both open and closed. There will be sets which are neither closed nor open. So hindi ito on and off, no? Parang eleksyon, hindi lang ito Lenny at Bongbong. Naintindihan nyo? Hindi siya dalawa lang. May mga sets which are neither open nor closed. Do you understand? Wag kayong mako-confuse doon kapag kasi may mga halimbawa may mga statements later. The set is not open. Ang mga estudyante, therefore it is closed. Naku. Pag nakita ko sinulat niyo 'yun, babalugbugin ko kayo. Hindi ganun 'yun ha, hindi 'yun yung logic nun. Ang set ay closed kung yung complement niya ay open. Halimbawa, yung X at yung empty set, mga closed sets yan. Alam niyo bakit? Halimbawa, ito closed set kasi ang complement ng X, empty. Eh di ba open to kanina? Kaya yung complement niya na X dapat closed. Ito rin ay closed kasi kapag kinuha yung complement niya, si X, which is open. Therefore, it's also closed. Kaya yung set na X tsaka empty set, they are both open and closed. No? Sa topology, tatawagin natin sila later as the clopen sets. Niwala man kayo or sa hindi ko kayo niloloko. Sa math, meron tayong word na clopen. They are called clopen sets. I'm not really joking. These are really mathematical terms that we don't have in the usual or standard English language. Ito yung mga terms na dinevelop natin sa math to address this kind of issues. A lot of subsets is neither closed nor open. For example, yung set of rational numbers is neither closed nor open. Alam niyo bakit? First, una, hindi siya open. Kasi, pag kumuha ka ng rational number, let's say you get a rational number, kahit na anong radius ang gamitin mo around R, no? Laging may irrational number dito, no? Naalala nyo density theorem? Yeah? So therefore, ito ay hindi magiging subset ng Q no matter how small epsilon is. So hindi ka makakagawa ng ball around R so that the entire ball is included inside Q. So Q itself is not open. Okay? Also, it is not closed. Alam niyo bakit? Kasi if you take the complement of Q, you get this time the irrational numbers. Same logic. Kasi kapag kumuha ka ng irrational number na Q at mag-drawing ka ng epsilon ball niya around it, no matter how small that epsilon is, lagi namang may rational number na nandito. Kaya ito can never be made part, hindi siya. Kaya itong ball na ito can never be made part of R minus Q entirely kahit gaano kaliit yung epsilon. Kasi lagi may nakakalusot na rational number sa gitna. So because the complement of Q is not open, ang conclusion is that Q is not closed. So as you can see, the set Q of rational numbers is neither open nor closed. Oy, anong nangyari? Oh my gosh. Ayan. Okay, this is an example of that. Now, using De Morgan's law, the following can be said. Kanina, arbitrary unions of open is open. Finite intersection of open is open. Pagdating sa closed, it's kind of the opposite. Kasi nga, ang definition ng pagiging closed, nakadepende lang naman sa pagiging open. No? Tignan nyo ngayon this time. Ang arbitrary ngayon ay intersection. Ang finite ngayon ay union. Baligtad. Kanina, kapag open, arbitrary union of open is open. Finite intersection of open is open. No? But this time, it's the opposite. Arbitrary intersections of closed sets are closed, and finite unions of closed sets are closed. The reason for this is De Morgan's law. Kasi tingnan nyo. Halimbawa, you get to have let's say this is a collection of closed sets. Kahit na ilan yan. Question is, why is the intersection closed? We're looking at the intersection. Kasi, if you take the complement of this intersection by De Morgan's law, it is going to be a union of complements. Right? De Morgan's law. This time, ito ngayon, open to kasi si F alpha ay closed. So yung complement na ay open. Eh di ba sabi natin ang unions ng mga open sets kahit na ilan is open. So kung ang complement nito ay open, therefore yung intersection ay closed. Actually, it doesn't need a proof anymore, no? Ganun din naman kapag finite union. Kasi if let's say you get x minus f1, f2, finite union hanggang fn, yan, ganyan. De Morgan's law is going to be a union of complements. X minus f1, intersection ngayon, x minus f2, intersection, x minus fn. Na yung mga complements na to ngayon, lahat open kasi bawat isa ay closed. Anong alam natin sa finite intersection ng mga open sets? This is open. And now because the complement of this complement is open, it means to say that this finite union is closed. Did you understand? So it's a matter of using what do you call that? Yeah. De Morgan's law. Going back, there is one more characterization, or there is one way to characterize closed sets. No? Instead of using open sets, no? We can make use of convergent sequences to somehow describe kailan nagiging closed ang isang closed sets. Naintindihan niyo? Kung ayaw yung gumamit ng argument using open sets, you can use arguments using convergent sequences to prove that a set is closed. Sabi, the following are equivalent. So si F pala, by the way, is a non-empty set of a subset of X, which is a metric space. The following are equivalent to F being closed. Ano yun? Sabi, kailangan every convergent sequence in F whose terms are in F must have a limit in F. Actually, sa totoo lang, dito kinuha, sa result na ito, kinuha yung word na closed. Di ba the way we think about closed in the English language is, it's like, it's closed, no? Sarado siya sa Tagalog. Sarado in the sense na kung ang open, bukas. Bakit bukas? Hindi kasama yung boundary. Ang closed ngayon, sarado, kasi normally ito yung mga sets na kasama yung boundaries nila. Alam niyo bakit tinawag na closed yan? Kasi ang sabi ng definition, ay no, not the definition but this result, kung meron ka raw sequence sa loob nung set na ito na magko-converge siya, no? Dapat yung limit mo nandun pa rin sa F, hindi lumalabas. Why is this even a property? Kasi hindi mo yan masasabi kapag, let's say, yung set mo hindi kasama yung gilid. Let's say, ganyan. Ano ba, ganyan yung set mo, no? Because kapag ganyan yung set mo, you can construct technically a sequence of points na magko-converge. Pero yung limit mo, wala doon sa set. Pwede kasing lahat ng terms mo nandun sa set, tapos nag-converge ka doon sa gilid. Na-imagine nyo ba yun? And when that thing happens, that's very sad kasi imagine mo, all your terms are in F, tapos nag-converge. Pero yung limit mo wala doon sa set. That's sad, no? Pero kapag closed set ang pinag-uusapan, hindi ka masasad. Kasi sabi, kapag closed daw ang isang set, lahat ng convergent sequence na matatagpuan mo sa loob ng F na ang mga terms, lahat nasa F. Yung limit nila nasa F din. And in fact, this is a necessary and sufficient condition para masabi na si F ay closed. If you want the proof, this is the proof. So you can see. So the proof, because we're proving equivalence, will prove that these statements imply one another. Okay, why does one imply two? So assuming F is closed, we will prove that every convergent sequence in F, whose terms are in F, has a limit in F. So what we do is we take an arbitrary sequence in F that converges to some point in X. So ang alam natin nasa F, yung X of N. Ang ating ipapakita dito is really to show that the limit X is in F. Para masabi mo to. Naintindihan nyo? Can I proceed? Kayo ba'y nandyan pa? Hindi ko kasi nakikita yung mga mukha nyo. So I cannot really assess if I'm getting fast or hindi katulad ng face-to-face. Nakikita ko sumisimangot na, no? So if you have questions, you can interrupt me if you want. No, hindi kayo na-gets, no? You can right away, I would like you to interrupt me kasi at least we have interaction. Problem is I cannot see your reactions like in a face-to-face class. So please, na lang, salita sa mic or chat box if you have something to say. So here, we're proving that X is in F. That's our goal. And we will do it indirectly. Kunwari wala si X doon sa F, ano mangyayari? Pag wala ka sa F, nasaan ka? Eh di nasa complement. Di ba? Nandun ka sa complement. Which is, by the way, open. Kasi si F ay closed. So imagine mo, open set ito. Si X ay naroon sa open set na to. Anong sabi natin doon? Hindi lang si X ang naroon. Pati yung mga points na nasa paligid niya, nandoon pa rin sa complement. Kasi open eh. Ano mo isusulat yun in words? There is some radius, ang gagamitin ko delta. There is some radius delta so that when you construct the ball around X with delta as the radius, it's still properly contained sa complement ni F. Parang imaginein mo, dahil si X ay nasa labas ni F at yung labas ni F ay open, sabihin, a little portion of things near X must still be outside F because the outside is an open set. Ang gulo, no? Yung ball mo nasa loob ng labas. Pero that happens in mathematics. Hindi yun magulo kapag sa context ng mathematics. The ball is a subset of the complement of F. So parang yung ball sa Tagalog nasa loob ng labas ni F. Okay. Pag yung ball nasa loob ng labas ni F, anong relationship ng ball kay F? Di ba isabihin nun, kung let's say ito si F, Ang nasa labas niya ito. Pag yung ball nasa labas ng loob, nasa loob ng labas ni F, sabihin yung ball mo nandito. Diba? Yan yung delta. Ano mo mapansin nyo sa F tsaka sa ball? Hindi sila magbabangga. So the intersection of the ball and F is empty. Right? Yeah. Set theory lang yan. Wala tayong ginawang magic dyan. It's really just set theory because the ball is in the outside of F. Then the ball and F cannot intersect. In fact, the intersection is empty. But, as you can see, it's given kasi na yung x of n nagko-converge x, hindi nyo pa nagagamit yun. So using the definition, one can produce a natural number n, or there comes a time afterwards or after which yung distansya ng xn from x is already less than delta. Darating yung time na yung distance n mas maliit na sa delta. Ano yung delta? Siya yung radius ng ball. No? Ito yung scenario. Papakita ko sa inyo yung remember, handahan tayo ng contradiction. No? This is f. This is x. Because the complement is open, I can create a ball around x that is what? That is really outside f. So they don't intersect. Eh may sequence ka na nagko-converge kay x. So, sabihin, after some time, yung isang term mo at yung mga susunod doon, nandiyan na sa loob ng open ball na yon. Yan yung sinasabi. Pero remember, this is the contradiction. Remember, lahat ng terms ng xn nasaan? Nasa f din. So, sabihin, si x sub capital N mismo, nandito rin sa f. Paano mangyayari yun, sir? Hindi nga sila nagbabangga. Yung ball, tsaka yung f, empty ang intersection. Paano merong point na present dun sa dalawang set? Exactly. Naghahanap kasi tayo ng contradiction. That's the contradiction. Kaya hindi pa pwedeng mangyari yun. Kaya dapat yung x nasa loob ng f. And just to finish everything, in particular, yung x of n nandun sa ball, at the same time, nasa f siya. Therefore, it's in the intersection, which is a contradiction to this. Therefore, x must be in f. So, we're done proving 1 implies 2. To seal off everything, we have to further prove that 2 implies 1. So this time, we will assume that every convergent sequence in f has a limit in f. No? And we are now proving that f is closed. Now the idea here is we will also proceed indirectly. Kunwari hindi closed yung f, ano mangyayari? Kasi di ba kapag f ay closed, by definition, yung complement ay open. So pag hindi ka closed, yung complement mo hindi open. Recall. U is open if and only if for every point in U, there exists a radius positive such that the ball around X with R as the radius is inside U. So pag hindi open, paano mo ine-negate yung statement na yan? Kasi kailangan natin yung negation because we have a statement here saying something is not open. So kailangan mo i-negate ito. Paano nag-negate ng for all? Anybody? Paano nag-negate yung statement na to? FCM2.
There exists.
Ayan, magiging there exists. Very good. Tapos yung there exists magiging
For all.
very good. Magiging for all. Wait lang ha, lakasan ko lang yung speaker ko. Yeah. Yan. So magiging ano to, there exists Sabihin, there will be a point. Now, dahil we're talking about a particular point, ang gagamitin ko x naught. No? There will be some point x naught in U such that for every r greater than 0, kahit gaano kaliit or kalaki yung radius mo, ano mangyari? Yung ball mo na ito ay hindi magiging subset ng, di ba talaga naman? Makakahanap ka raw ng isang point doon sa set, kung hindi siya open ha, kung saan at that point, mag-construct ka ng ball, maliit o malaki ang radius, yung ball na yon hindi makakapasok ng buong buo sa U. Yun yung sinasabi no. Make sense? Ay, ang galing. Tama pala yung tinuturo sa logic, no? Oo. Naintindihan niyo? Kaya kayo tinuturuan ng mga logical quantifiers nun kasi there will really come a time na gagamitin niyo siya in mathematics. It makes sense now. So, dito natin siya gagamitin. There will be some point in the complement of f so that no matter how small the radius is, ang ginamit ko pala ay epsilon. Kasi pag for all, karaniwan ang kapartner epsilon. Pag there exists ang kapartner karaniwan delta. Hindi ito standard rule or hindi ito talaga rule, but it's more of rules ng technical writing or to make it more readable. Hindi siya mathematical rule. It's just a rule to make readings easier. Pag nakita mo yung epsilon, laging kadugtong nun for every, di ba? Pag delta, laging there exist. Parang standard na ano yun. Yan. So there will be, oh my gosh, there will be some point in the complement so that no matter how small the radius is, this ball will not be included in the complement. So just like before, pag walang slash to, di ba pag nasa loob ka nung labas ni F, sabihin, hindi ka bumabangga kay F. So in short, pag hindi ka entirely nasa labas ni F, ibig sabihin, bumabangga ka kay F. Diba? When bumabangga ka kay F, may intersection yung ball tsaka si F na hindi empty. In other words, there is some point in this intersection, no matter how small epsilon is. Did you understand me? Sa set theory kasi A is a subset of B complement if and only if A intersection B is empty. That's the underlying idea. Okay? Okay. Can I proceed? Yes or no? Okay. Ito, sasamantalahin natin ngayon to. The fact is, kahit palitan mo man tong epsilon ng kahit na anong positive na number, kahit 0.1, 0.01, 0.0001, kahit gaano kaliit yan, imaginein mo kahit gaano siya kaliit, nag-i-intersect siya kay F. Parang kung iisipin mo, ito si F, nasaan yung x0 na yan? Yung x0, nasa complement ni F, tapos, pag gumawa ka ng kahit na anong ball around it, kahit gaano kaliit yung radius, laging nag-intersect kay F, parang mali yun, sir. Mali talaga kasi naghahanap tayo ng contradiction, remember? Kasi tignan nyo, sa una, oo, talaga nag-intersect kay F. Check. Pero tignan nyo, as I make the radius smaller, darating yung time na hindi ka na mag-intersect kay F. Parang may something weird, no? Something is wrong. There must really be something wrong kasi remember, we're looking for a contradiction. That's what you wanted to point out in the proof. Naintindihan niya? This is what I do. Look at this. Ang gagawin ko, ganito ang step by step. Let epsilon be 1. So, dapat yung ball around x0 with radius 1 nag-i-intersect kay F. No? So kung nag-intersect kay f, ibig sabihin makakapili ako ng x sub 1 sa loob. Next, let epsilon be 1/2. Yung ball around x naught with radius 1/2, mag-intersect ulit yan kay f. So ibig sabihin may point ulit sa loob. Naintindihan nyo? The idea is, nasan dapat yung x naught? Yung x naught hindi pa pwedeng nasa labas ng f kasi ganyan, no? The idea is, kapag ito'y 1, meron ditong x sub 1. Pag ito'y 1/2, meron dyang x sub 2. Pag ito'y 1/3, meron dyang x sub 3. And so on. Pag yung epsilon ay 1/n, makakapili ka sa loob, tawagin mong x sub n. Anong nagawa nyo ngayon? Ang nagawa natin ay sequence. Meron kang x sub 1, meron kang x sub 2, meron kang x sub 3, at itong katotohanan. Because yung x sub n ay nasa ball na yan, yung distansya na itong dalawa, hindi aabot ng 1/n. And by the squeeze theorem, ang 1/n kasi lumiliit na lumiliit, habang lumalaki n. Ito naman, hindi naman nagne-negative yan. This has to go to 0. And that should mean x sub n must converge to x naught. Diba? Ano ba sabi ng assumption? Sabi ng assumption, pag merong sequence sa f na nag-converge sa isang point, dapat yung limit na yun ay nasa f. So what's the conclusion? By assumption, x naught must be in f. But you know, this is the contradiction. How come x naught is in f when in the beginning, x naught is not in f? Diba? In the beginning, in fact, the very fact na nag-exist si x naught, nag-exist siya dun sa complement ni f. But then after some argument, you find that the point is in f. That's wrong. No, you cannot be in the set and its complement at the same time. With this contradiction, what we suppose cannot be true. Therefore, f must be closed. Nasundan niyo yung proof? Ang importante, nasundan niyo yung proof. Huwag niyo isipin kung may isip niyo mag-isa yan. Nasundan niyo yung proof? Ako, the way I want you to remember this, kaya ako i-present ito, kasi ang mga closed sets are special because they keep limits of convergent sequence within itself. Sarado siya, meron siyang barcode. Kung magko-converge, kung meron kang sequence sa loob na nag-converge, yung limit mo hindi makakatakas. Naintindihan nyo? Naintindihan niyo yung idea ni Sir? Kasi ito yung mga ideas ko na hindi nyo mababasa sa mga libro. Kasi pag kayo nagbasa lang sa libro, ito lang ang makikita nyo. Authors normally, especially in higher mathematics, are very lazy to explain. Dali lang. Ano? Naintindihan nyo? Nasundan nyo? Can I proceed? Okay. So tapos tayo sa convergence, sa mga Cauchy sequence. Puro C yan eh. Ano yung convergence, Cauchy sequence, closed sets. Alam nyo kung ano yung susunod? Letter C din. Maraming C sa analysis eh. Continuous functions. Okay. So this time we're now looking at functions. Sa analysis, ang mga functions of importance, hindi lahat ng functions ay pinag-aaralan sa analysis. We are normally interested with these functions which are called continuous functions. Now, ang mga functions natin dito, not necessarily kasi na R to R ang mapping, no? R to R. Kaya hindi necessarily may mga graphs ka na katulad ng mga graph na nakikita nyo. Kasi the way we think about continuous functions, remember in elementary calculus days, no? Ito yung mga functions na pag rinaf mo hindi napuputol. But this manner of looking at continuous function will not be so useful in this course, no? So pag continuous ang function, tanggalin na natin, wag tayo masyadong mag-rely sa idea na ang continuous function siya yung function, ang graph ay continuous. Pag ang function, tayo nag-uusap ng function sa subject na to, huwag niyo siyang iisipin as a graph. Sa course na ito, makakatulong kung iisipin nyo na ang continuous function, para kang naglalaro ng clay. Yung x mo kunwari, let's say meron kang clay, yun yung x. Gusto mo siyang i-convert into another figure y, no? What do you do? Let's say may clay ka na hugis sphere. Gagawin mo siyang cube. For example, what do you do? At ipipisa-pisain mo yung clay, di ba? I-ano mo siya. I-demold mo siya hanggang maging cube, no? Yung action na yun, yung nagde-deform ka ng sphere para maging cube, think about it as a continuous function. Continuous kasi hindi mo siya binubutas, hindi mo ginugupit, no? Hindi ka gumagawa ng butas, hindi mo pinupunit. Yun yung mga importante kapag continuous. Okay? I want you to think about it that way instead of looking at it. Kasi itong mga ganitong approach kasi sa calculus to, kasi we're talking about functions from R to R. This is it really helped us in studying calculus before, but this time it will not be so useful. So this is our definition. Kung babalikan nyo sa pangbatang calculus, no? Babalikan nyo sa pangbatang calculus, no? Meron kayong 3-step test, di ba? For continuity. F is continuous on a set X. Ganito na lang. Continuous if and only if F is continuous at every X in X. Ang tanong, ano yung sabihin ng F is continuous at X? Sa calculus dati, meron kayong 3 test. If you can remember, no? Anong kailangan? Una, dapat yung F of X nag-exist. I don't think X ang magandang gamitin. So, can I use some other letter? Let's say A. Kailangan ito yung nag-exist. Pangalawa, dapat yung limit nag-exist. Pangatlo, dapat yung nasa number 1 tsaka yung nasa number 2 ay equal. Kailangan yung functional value mo nag-agree dun sa value ng limit. Kasi this will tell us na yung graph ay hindi tumatalon or walang butas, right? Ito yan sa calculus sa pambata. But if you're going to look at this, parang ang sinasabi niyan, yung f of x lumalapit sa f of a kung yung x palalapitin mo kay a. No, ganyan yan eh. Pag yung x palalapitin mo kay a, yung f of x lumalapit sa f of a. Parang the limit of the images is equal to the image of the limit. So parang yung x ay lumalapit sa a, yung image niya lumalapit dun sa image ng limit. Kaya ang continuity, you can say it as a function that so that the image of the limit of the images of points are equal is equal to the image of the limit. Parang napapagpalit mo yung image of the limit, limit of the image. Right? Pero formally, this, as you can see, related dyan eh. Related dito yung definition natin na nasa taas. Tignan nyo. A function f is continuous at x if for every epsilon greater than 0, there exists a delta greater than 0. Mga positive number lang yan. Pero remember, sabi ko, huwag magpapa-intimidate dyan. Something less than epsilon, isipin nyo maliit. Something less than delta, isipin nyo maliit. Saan sinasabi niyan? Yung image ng f of p malapit sa image ng x under f if whenever yung p mo ay nasa x at malapit siya sa x. Kumbaga, pag meron kang dalawang points doon sa image space, pag meron kang dalawang images na malapit, dapat nanggaling sila sa dalawang malapit na points. Ang pinanggalingan nila ay dalawang points na malapit din. Hindi pa pwedeng nangyari na ang dalawang points malapit kanina pero yung images mo malayo sa isa't isa. That cannot be the case kung continuous ang function. Alam nyo bakit? Kasi pwedeng ang ginawa mo, pinunit mo yung space. Pag kasi alam ba, may papel ka, pinunit mo sa dalawa. May dalawang points na kanina na malapit na pinaglayo mo when you tear the paper apart. Do you understand me? Let's say, ito yung piece of paper. Then, ang ginawa ng function, kunwari pinutol mo siya into two parts. No? You tore it apart like this. If you look at, let's say, ito yung P, ito yung X. Kanina, malapit sila. Pero dahil ito yung cut na gagawin mo, pinutol mo siya dito, pinutol mo sa gitna. Ang nangyari ngayon, ito na si P, ito na si X. Ngayon, this time, they are not, no, this is not P, sorry. This is f of P, this is f of X kasi nakarating ka na sa image space. Nakita niya? Naintindihan niya si Sir? Bakit sinasabi ni Sir na kapag continuous ang function, bawal lang nagpupunit, bawal lang nagbubutas, kasi it might affect distances between points. Kung kanina malapit kayo, baka dun sa image space, hindi na kayo malapit. Naku, problema. Hindi yun continuous. Pag continuous, things that are near, parang somehow, Hindi. Pag continuous, pag malapit kayo dito sa image space, dapat ang pinanggalingan nyo ay dalawang malapit na bagay. Naintindihan nyo? Pero ito ang ating definition, or working definition. For every epsilon, dapat makakahanap ka ng delta so that you can force these two to be close to one another at a distance less than epsilon as long as as long as P is taken to be this close from X. Okay? Equivalently, it's continuous at X if and only if for every open ball B sub Y around f of X. Kasi as you can see, this defines an open ball. Yung mga points na nakakasatisfy dito, no? This is an open ball around f of X with radius epsilon. Dapat may open ball around X. Ito yung open ball na yun. Ang radius ay delta so that yung image ng open ball na yan ay subset ng open ball na B sub Y. In pictures, this is what I want, how I want you to see it. Ito yung X, kunwari, let's say after the transformation, ginawa mo siyang oblong na ganyan. No, yung rectangle naging oblong, kunwari. Continuous yan sa X. Kung, ito kunwari si X, no? Siyempre meron siyang corresponding, nakikita nyo ba yung X at f of X? Kasi medyo odd yung choice of color ko. Do you see X and f of X? Kasi sometimes in my slides I can see it, but when flashed through Zoom, minsan na-distort yung color. Can you see it properly? Okay. Thank you. Sabi ng definition, dapat, anong sabi? Pag gumawa ka ng epsilon ball around f of X, naku, lalo nang naloko yung choice of color ko, hindi yata nakita yung f of X. I hope you can see. So this is an open ball around f of X with epsilon as the radius. Dapat for this ball, makakahanap ka ng delta ball around X So that, ito yung mangyari. Pag kumuha ka ng something dito, let's say P, dapat yung f of P mo nandito sa loob. Naintindihan niya? In other words, yung image ng buong open ball na ito should be found somewhere here. Hindi man siya ball na, maaaring hindi na siya open ball, maaaring hindi na siya ball, pero yung entire image niya, which is this, kailangan na sa loob ng red ball. Did you understand? Okay? At we simply say that the function is continuous entirely if it is continuous at every point in its domain. Sabihin kung nangyayari yung idea na to for every x. If this is true, so if this happens for every x in this space, let's say lumipat ka dito, ito yung x, ganyan pa rin ang nangyari, gumawa ka ng ball, makakagawa ka pa rin ng ganun. Fine. Continuous yung function. Pag sinabing f is continuous, walang reference kung saan, sabihin nun is continuous everywhere or at every point. Okay? Okay, ano bang mga examples ng continuous functions? Ang pinakasimpleng example, mga constant functions. Anong sabihin ni sir ng constant functions? Let me just, wala kasi yan sa slide ko, but okay. Anong sabihin ng sir ng constant functions in this context? Kasi pag kunwari ito yung x, ito yung y. Pag sinabing constant, hindi naman kailangang real numbers ang pinag-uusapan. Pag sinabing constant, yung image ng bawat point doon sa domain ay isang point lang. Kumbaga, all the things that are in X are being mapped to a particular point in Y. Yan ang ibig sabihin natin ng constant. Na? Constant yung value ng F. Why is this continuous? You know why? Kasi pag kumuha ka ng X dito, kahit na sino si X, di ba? Ang F of X mo, why not? Di ba? Lahat pupunta dito. Kaya kapag gagawa ka ng open ball around here, pag kumuha ka ng epsilon greater than 0, actually kahit na anong delta ang piliin mo dito, mag-work. Kahit anong delta. Alam niyo bakit? Anyway, lahat naman nagpupunta dyan sa y naught. Yung image na itong ball na ito, talaga naman papasok sa loob kasi ang image na laging isang point lang, laging y naught. Did you understand? Bakit ang mga constant functions are the basic examples of continuous functions. Well, to further describe continuous functions, meron akong characterizations or different ways to characterize constant functions. Okay? Ano yung different ways? Ito. Meron pala tayong iba't ibang paraan para tignan ng mga continuous functions. Number 1, by looking at sequences. Ito yung number 2 pala. Number 3, by looking at the open sets. And number 4, by looking at the closed sets. Ano sabi? Tingnan. Ang function daw na f from x to y ay continuous kung may convergence na nangyari kay x. Let's say, si x sub n nagko-converge kay x doon sa capital X. Yung image nung sequence na to nag-converge sa image nung limit doon naman sa y. In short, ang mga continuous functions ay nagpre-preserve ng convergence. Di ba common theme ito, di ba? Kapag kayo nasa group, ang mga homomorphisms nagpre-preserve ng operations. Pag kayo nasa calculus, ang mga continuous functions nagpre-preserve ng convergence. This is a common theme in mathematics. Whenever we're talking about a particular object, the next thing to look at are the functions that relates between them. Tapos, tinitignan natin ano yung mga properties ng space na hindi nawawala upon the transformation. This is a common theme in mathematics. I hope you can see the big picture now. No? At this point, dahil medyo marami-rami na kayong experience sa math, dapat nakikita nyo na yung commonality ng mga math subjects. Okay, what does it do to open sets? Sabi, if you get an open set, let's say X, this is Y. If you get an open set in Y, and you look at the inverse image, when you say inverse image, ito yung mga points na nagpupunta sa U, pero nasa domain. Dapat yung inverse image niya ay open. So dapat yung mga open set sa Y, ang sinasabi niyan, nanggaling sa mga open set sa X. Hindi pa pwedeng manggaling ang isang open set sa Y sa isang set na hindi naman open sa X. Naintindihan niyo? And that is also true for closed sets. Kailangan ng mga closed sets sa Y ay manggagaling sa mga closed sets na nasa X. And these are all equivalent formulations of being continuous. Again, we're talking about metric spaces over here. Kaya kung pinapakita yung mga results na to, kasi again, in the future lessons, you will see that these statements are no longer equivalent. May no longer be equivalent, especially yung number 2. Parang hindi na sila equivalent sa isa't isa. Pero ngayon, enjoyin muna natin kasi mga metric spaces pa lang. No? I mean, magaganda pa yung mga spaces na pinag-aaralan. So, yeah. Later, you will see that this, in particular, itong dalawa may no longer be equivalent. So, the idea is this. Ito yung gagawin natin to prove the equivalence. I will prove that the continuity proves number 2. 1 implies 2. And then afterwards, I will prove that 2 implies 4. Kasi remember, ang convergence may kinalaman sa pagiging closed, di ba? Tapos, ang mga closed sets related sa openness, kaya ipoprove ko yung 3 gamit yung 4. And finally, by the Ball's characterization ng continuous functions, gagamitin ko yun to prove 1 from 3. So meron akong cycle, no? 1 to 3, 3 to 4, 4 to 2, and then, 1 to 2, 2 to 4, 4 to 3, and then 3 back to 1. That's how I prove the equivalence. Ito muna yung 1 implies 2. The map F is continuous. So this is the assumption. Now you get a sequence x of n converging to little x in capital X. I want to show that f of xn, ito yung kailangan natin pakita, magko-converge f of x kay y. To prove convergence, we always begin with let epsilon be greater than 0. Assumption ito. Sasamantalahin natin na nagko-converge si x of n kay x. By the way, ano pala? Dahil pala si f ay continuous sa x, nandun yan sa x eh. Diba? By the continuity, there you can select a delta greater than 0 so that this distance in y, kaya kung nilalagyan ng subscript na y, kasi may dalawa ka ng metric spaces, may dalawa kang metrics. May metric kay x, may metric kay y. Okay? The distance in y of these 2 points is made less than epsilon. Basta si p ay pipiliin mo sa x na ang distance from x sa capital X ay less than delta. Okay? Now, look at this. Dahil nagko-converge x of n kay x, by the definition of convergence, one can select an n so that I can force this distance, the distance between 2 to be less than delta paglagpas ng n. So if you now select an n beyond capital N, then yung distance nito ay less than delta, diba? So it's less than or equal to delta. At dahil yung x of n ay nandun naman sa x, sabi ng continuity condition, pag kasi yung p nasa x at ang distance mo from x is less than delta, dapat ito'y totoo. So dapat yung distance in y ng f of xn tsaka ng f of x dapat less than epsilon. Tapos na. This proves that f of xn converges to f of x kasi we were able to make this less than epsilon for big values of n. Madali lang. I mean, it's just direct applications of definitions. This time, ipuprove ko yung 2 implies 4. Ang gagamitin ko ditong connection ay yung sequential characterization ng pagiging closed na sa loob ng isang closed sets, ang mga convergent sequences may limit na nasa loob pa rin ng set. So ganito. So f ay closed sa y. Puprove natin ng f inverse of f, capital F, ay closed pa rin sa x. Kung ang assumption ay nagpre-preserve ng convergence yung f. Okay, so let f be a closed subset of y. Ang gagawin ko to prove that this is closed, I will pick an arbitrary sequence here na nagko-converge to some point. If I can show that the limit is still here, that's equivalent to proving that the set is closed. Remember? Yan. Kaya nga ang gagawin natin, we will prove that the limit x is in this set para masabing closed siya. So this is what I do. By hypothesis, dahil yung x of n nagko-converge kay x, sabi ng assumption, yung f of x yun nagko-converge kay f of x. Right? Eh dahil si f ay closed, tapos lahat ng x of n, nasan ba yung x of n? Yung x of n, lahat nandito sa inverse image ng f. So if I take the images of each one of these, nasa capital F yun for all n. E nagko-converge to, tapos si f closed. Oh my gosh, ano sinasabi nun? Sa f ay closed, lahat ng terms nasa f. So yung limit mo, dapat nasa f din. And with this in mind, it only shows that the point x is also in the inverse image of f. And that concludes the point. So the fact na yung limit ay na-prove natin to be in the inverse image of f, that means the f inverse of f is closed. Okay. Next, how do we connect 4 to 3? Anong relasyon ng closed at open? Yes, ang complement ng closed sets ay open sets. Ang complement ng open sets ay closed sets. So we make use of, what do you think? This is what I do. So I pick an arbitrary u in y. Then because u is open, its complement in y is closed in y. Okay? Dahil closed ito in y, sabi ng hypothesis, pag kinuha ko yung inverse image nun, closed yun in x. Diba? Ano mangyayari? Eh kaya lang, yung f inverse na to, by properties of functions, yung f inverse ng complement ay complement ng f inverse. Ganun yun. Kaya yung inverse image ng complement ay complement sa x ng inverse image. So ano to? Ano tong set na ito? Yung set na ito ay closed in x. Kung closed yan in x, pag kinuha ko yung complement yan in x, anong lalabas? Dapat open. Kaya lang, ano yung complement ng complement? Pag dinoble mo yung complement, nawawala yung complement nila. F inverse of u. So ano to? This must be open. Tapos na. And to finish the proof, we will prove that 3 implies 1. Assuming that the inverse image of open sets is open. Okay, that's the idea. Bakit ngayon continuous yung F? So, paano mangyari yun? Ito na may epsilon delta. Na gagamitin natin epsilon delta definition of continuity. So, I will pick an arbitrary point kasi we have to prove the epsilon delta for every x in the domain. So, I let an epsilon be greater than 0. The idea is to get a delta greater than 0 so that blah, 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 blah in definition of continuity. Ang gagamitin ko, ganito gagawin ko. I will consider, ito yun x y, may x ako, meron akong f of x. I'm going to look at the open ball around x with epsilon as the radius. Ang mga open balls open, right? Yeah. So by assumption, kung ito ay open, tatawagin kong u yan. I will look at the inverse image of u. By hypothesis, yung inverse image na yun ay open sa x. So dapat nandito yan. Kaya lang saang banda yan ng x. You see that u is open in y. So by hypothesis, yun nga ay inverse image ay open din sa x. Ang tanong, saang banda yan ng x? First of all, First of all, yung x nandyan sa f inverse kasi yung f of x mismo ay nasa loob ng ball na ito. In short, yung f of x ay nasa u. Kaya yung x mismo nasa inverse image ng u. Si x mismo yung kauna-unahang nandyan sa inverse image. So, hindi yan empty. Thus, dahil ito'y open at yung x ay nariyan, by the definition of openness, you can construct a ball around it with delta as the radius so that this ball is entirely inside u. No? Tama ba? Parang mali tayo dito. Mali ito. Kita nyo? This is not u. This is f inverse of u. Okay, can you please take note of the error? That's f inverse of u. Kaya nga naging ganito yan. F inverse of the ball. Okay? So now, dahil ito is subset nito, if I take a p over here, if I take a p there, no, dapat yung p naririto. Eh pag nandyan yung p, sabihin yung f of p nandoon sa ball. O sige niyo, i-rewrite nyo itong dalawa. Pag i-rewrite nyo yung dalawa, pag yung p nandito sa ball, sabihin yung distance in x ng p at x less than delta. How do you rewrite this one now? Yung distance in y ng f of p tsaka ng f of x less than epsilon. O diba yan yung definition ng continuity? And that proves that f is really indeed continuous at x. Okay? Now, this is the end of this lesson. So for the next lesson, we are going to talk about topological spaces. We shall now start the course proper. Again, ang reason kaya tayo nag-aral na metric spaces to compare the more general situation with the most common situation. Ang most common situation yung metric spaces kasi ito yung kinalakihan nyo. Diba? Ito yung kinalakihan yung analysis. You will find that some of these results are still consistent. Some of these results does not really hold in general. And aalamin natin, ano yung property ng para mag-hold itong mga results na ito. So that's the idea of the next few lessons. Before we end the session today, I'd like to announce something. Pero stop ko muna yung recording.